Okay guys, let's get started. Let's get started with today's lecture. Today I want to talk to you a little more about networks. So the last time I introduced you to social networks for the first time. Now we're going to talk a little more about that. And then I want to spend some time on what we call the friendship paradox. Partly also, it fits in what we're doing over here, but partly also because I've done some research on this in this field. So I think it's always interesting to see, what us guys are doing here. But it also feeds in very nicely with the overall context of the lecture. Okay, before we start, just an announcement. I need to be reminded of these kind of things. Somebody needs to tell me because otherwise I would show up. So on Friday there's Easter. There's Good Friday, so we don't have a lecture on Friday. Yeah. So after this lecture, the next one is again on Tuesday. So there's 1 week in between. And we're slowly getting towards the end of the term. So actually next week, I hopefully will give you some feedback on the assignment. You remember, you had to hand that in a while. By now, all the latecomers are in as well. So hopefully there's going to be some group feedback on that. But then I will provide an opportunity for individual feedback as well. But I'll talk to you more about that next week. And also to keep in mind, the next take-home exam is coming up as well. Same spiel like we had the last time. It's going to be like a similar format like the last time. You know now what to expect. So if I were in your position, I would use the time now already to catch up on the readings that you haven't done yet. So the required readings on Blackboard, they are relevant for the exam as well. So it actually makes sense. Okay, let's get started or continue with networks again. So this is sort of like this notion that I introduced. We are talking about relational data. Social networks are relatively easy to think about. Like individuals are connected with each other. They might be friends. They might ask each other for advice. That's sort of like traditionally what people looked at. But it could also be different things. It could also be about bullying. Who bullies whom? Yeah? So for example, right now I have a research project where we look at teenagers. We look at who bullies whom and how that is related to obesity. Yeah. So that's sort of one of the things you can look at. But you can even move beyond social networks. You can think about or individuals. You can think about organizations being connected with each other. Yeah? Or you can think about countries being connected with each other through trade agreements, for example. And once you kind of get behind that idea of relational data, you see these dependencies all over. Yeah? And I think in sociology, they're actually very important. So anyway, so I introduced a few things about social networks before. I'm going to continue talking about that. So I want to talk about these things today. So first I'm going to talk a little bit about distances and paths, just for you to get a feeling again for the kind of research we can do here, but then also to prepare the grounds for what I actually want to talk about today, which is the friendship paradox. But in order to understand that, you need to know what is centrality in a network. Yeah? So we need to know that. I talked about that the last time already. I'm going to talk about it again a little bit. And then the friendship paradox is essentially this very strange phenomena that if you take a random person and we look at how central that person is, that on average the friends of that random person will be more central. So if I apply that to you, if I take a random person here in the room, on average that random person has fewer friends than the friends of that random person. It's a little odd. But hopefully you'll understand this after this lecture. And actually I followed up on this and I did some additional research on this because we know for 30 years that lots of things correlate with individuals' positions in networks. Actually there's a whole research strand about what does a structural advantageous position do to individuals. They are more successful in life, they get better jobs, there are all sorts of things that are related with that. Finally, physical attraction is related to it too. Yeah? So research shows that there is a correlation between physical attraction and the number of friends that you have. Well, if you put these two things together, you're going to see at the end of the day, and you take the logic of the friendship paradox, and that's actually the kind of stuff that I did in my research. I put these two things together. Then it's not only this weird phenomena that your friends on average tend to have more friends than you, but they tend to be better looking than you as well. Okay, but we're going to get to that point, and we're going to get a little mind-boggled with it. Anyway, so let's get started and talk a little bit about distances, and paths. Maybe you came across these kind of things before. 6 degrees. We are all linked with everybody else in the world through 6 connections. Who has heard about that before? 6 degrees? Hands up. Hands up. Okay, so some of you have heard about that. So basically, it's this idea introduced by Milgram at the time. He did this experiment. Basically, that a random person, a name on it, and he gave it to some random people in the States and said, okay, find a way to send this letter to that person. They didn't know that, but they knew some people. And then let's say, okay, well, I might send it to a person who I know, who I think who might know him, or who might know somebody else, and so on. And actually, if you would map that out, in this world, I think now we have 7 billion people living on this planet. Take any 2 people in the world, any random person here in the world, any random person anywhere else in the world. On average, it only takes 6 steps to connect you. A step is like somebody who you know, that's a step. A friend of yours is a step. Then a friend of your friend, that is another step. And then a friend of your friend is another step, and so on. So 6 steps on average it takes to connect any 2 persons in the world. That's a little crazy. How the hell can that be? That's actually what we call small world phenomena. We live in a small world. Actually, we do live in a relatively small world. And it's even more bizarre when you think about the fact that your friends often are connected with each other. It's like a small little group. So, I don't know, we're all here, we're in Dublin and so on, and, we might know each other or not. And, there's small little groups, and there's other little groups. I have, some friends in Germany, they're all connected with each other somehow, or some friends in the UK, and they're all connected with each other, and so on. So it's like small little groups, small little communities. But at the same time, so we have this feeling, this impression of what we call local clustering, or small little groups that we are embedded in, where everybody knows everybody. But we still have this strange phenomena that it only takes 6 steps to reach anybody else in the world. And the solution to this is that you have some random links. For whatever reason, I happen to know somebody in Australia. So now, I don't know, you know me, I happen to know somebody in Australia who actually might know somebody in New Zealand, who might know somebody in Tasmania or whatever, and that's sort of how we ended up there, very quickly. So a few random links generate this phenomena. And there's a whole literature on small worlds, introduced by Duncan Watts and Steve Strogatz back in the time. It was made a huge splash because it sort of was a very interesting phenomena to also they found a way to explain this, how this can be. And their solution was, it's basically some random links. A very small number of random links connect to achieve that behavior. So they started in a very artificial setup, like in a simulation environment where all there was like these very local links. There was no link to anybody else. It's basically like a computer experiment that they did. They artificially generated networks where only people were connected with their friends and they were connected with each other and so on. And then they started to introduce some random links, some completely random picks between 2 people. And only a very short number of random links suffice to generate exactly this phenomena, that you have this local clustering and then you have what we then call a very low average shortest path length, like a very short distance between 2 individuals. But we'll come back to that in a second, and maybe you get the idea. So there are a bunch of other popular science books, linked, connected. These things are funny. Actually, I like reading these books, but after a while, it's kind of the same kind of stuff. But nevertheless, I can recommend these things. I want to introduce you to the idea of paths and distances and hammer that point home with an example that I didn't make up, but that's sort of actually in the literature. For whatever reason, it became popular in social network analysis. Maybe we are just funny, I don't know. So it's called the Oracle of Bacon. The Oracle of Bacon. This is Kevin Bacon. Who knows Kevin Bacon? He's an actor, basically. Yeah? You might have seen him in some movies and so on. So I'm going to show you the Oracle of Bacon, which is a website. Okay, so that's the Oracle of Bacon. So you can take Kevin Bacon, and then you can type in any other actor. Yeah? For the fun of it, I just tried it out earlier with Liam Neeson. Just because I like the guy. Okay, what do we see now? Now we see that Liam Neeson was in a movie, he featured in a movie in 2014, The Nut Job, where there was another actor called Brendan Fraser, who also acted in a movie called The Air I Breathe, 2007, where Kevin Bacon was in the movie. And so this sort of shows us now how is Liam Neeson connected to Kevin Bacon through co-appearances in movies. This is actually now, we call this now a Bacon number of 2. It takes 2 steps to connect Liam Neeson to Kevin Bacon. In science, we actually have a similar version of it. We have Erdos numbers that people get for how many steps are they away from having co-published with this mathematician, Paul Erdos, who was who introduced the whole idea of random graphs. But coming back to so you can play around with the Oracle of Bacon and connect some other people with each other. But the whole idea is to think about these distances in the network. Yeah? Like how many steps does it take to connect 2 individuals in the network in the shortest possible way? And that's what we call the shortest path. The shortest path is sort of like the fastest way you can get from the one to the other. For example, the red line, that's the fastest way you can get from individual number 15 to individual number 17. Yeah? That's what we call the shortest path. And in this whole small world literature, that's sort of what they looked at. How many steps does it take? And then you can calculate the average shortest path, which is basically you look at all the connections that there could be, all possible combinations of getting from individual 15 to 17, but also from 15 to 13 and whatnot. And you actually have a lot of combinations here. And for each one of them, you can calculate the distance or the shortest path. And then you can take the average over all of those shortest paths, and that gives you the average shortest path. And if you would do that in the world with 7 billion people, the result would be 6. That's sort of like where this is coming from. Maybe just a little side note. So how do we calculate these shortest paths? This is actually where matrix algebra is actually very useful. Yeah? So don't freak out about this. Yeah? But it's actually very straightforward. Last time I showed you can think of the network as a matrix, with rows and columns, with zeros and ones. And if you would multiply the network, this matrix with itself, it would basically give you new scores for when you can connect 2 individuals in 2 steps, because it's 1 in the first step and 1 in the next step and so on. And you can keep doing this. And if you multiply the network with itself 3 times, it tells you which nodes can be connected with 3 steps. And then you can do it 4 times, and then it tells you which nodes can be connected in 4 steps, and so on. And you keep continuing like that, and then you populate the matrix, and it kind of then gives you something like this, which is a distance matrix. Yeah? So now I have a matrix of distances, basically telling me, now you see a short little network here. This is like a cute little one with 5 nodes, and there's sort of like arrows attached to it. It could be friendships, it could be all sorts of things. Now we are abstracting from this a little bit. And now these numbers tell me how many steps it takes to get from one individual to the other. For example, this is always about the row actor, that's sort of like the starting point, and the column actor, that's the end point of this. So this number here, 2, for example, tells me that it takes 2 steps to get from individual number 1 to individual number 4, which is the column. Now, when we look at number 1, here we are, you can count. There's a direct connection here. But maybe you notice this is a directed arrow. Yeah? So there's actually, you can't get from 1 directly to 4. You can get from 4 directly to 1, but you cannot get directly from 1 to 4. But what you can do, you can get from 1 to 2, and then from 2 to 4. So that means 2 steps to get from 1 to 4. And you can do this with all sorts of combinations. For example, from the 5th individual to the 3rd individual, it takes 3 steps. Here we are, actually 1, 2, 3, or actually now there are 2 possible ways, 1, 2, 3. Actually there's a 4th path, 1, 2, 3, 4, but that's not the shortest path. So that's sort of how we can calculate these distances, and then if I just take the average over all of those numbers here in this matrix, I would end up with 1.8. So here you would say the average shortest path is 1.8. And that tells you something, okay, how connected are individuals in this particular network. Okay, let me jump over this distance distribution and whatnot, but I want to talk a little more about centrality. So I started talking about that already the last time. Centrality is this idea that we want to know about how well are individuals connected. What is a structurally advantageous position? Yeah, they are important. And you look at a graph, you would say, okay, this guy is important, or that guy is important, or that guy seems to be in the midst of it in a way. But how do you quantify these kind of things? And actually, a lot of research, as I said, has been done in that area in connecting the structural position of individuals with all sorts of outcomes, like getting jobs, people being better informed, having higher status. Yeah? All these things where you would say, okay, of course networks matter. When you're more connected, you have an advantage of it. So you need to know, okay, what is that advantage, or how can you actually measure that the network position? And it's actually not that straightforward, as I tried to introduce the last time. What is well connected? Yeah? What is it? It could be, and some of you guys had that idea. I asked that question the last time. It could be simply the number of friends that you have. And actually, that's, as it turns out, that's the most straightforward way of measuring centrality of individuals. We call that degree centrality. It's really just the number of friends that you have. For each individual, they have a certain number which corresponds to how many friends that they have. Actually, we can then even distinguish between what we call in degree and out degree. In degree would be how many of those, we call them ties or arrows, point towards you. Like how many people nominate you as a friend. And out degree is how many people do you nominate as your friend. Yeah, you can see these things do not necessarily have to be the same. Yeah, there can be a distinction. People sort of are very popular, but they wouldn't call other people their friend, while in fact they do. So there can be a discrepancy about that. Degree centrality here, now you see a little example. When there are no arrowheads attached to it, now you see a little graph with no arrowheads to it. We call that an undirected network. Then you see then this in degree and out degree, it's exactly the same. So there's no difference between incoming and outcoming relationships. So anyway, so you see this little graph, 5 little nodes, and very straightforward. You could say, okay, individual A in the middle, that guy seems to be important. Yeah, and now we can actually look at degree centrality. If we would count how many links are attached to each individual, then you see for A it's 4, for the other one it's 1. So that's degree centrality, which I think is relatively straightforward. We can, then look at the distribution of this and characterize the whole network and how many individuals are with high or low in or out degree centrality and so on. Anyway. But as I started to talk about the last time, there are sort of different notions about what central means. There could be different ideas about what central is. Maybe central means being close to others, so that I can spread information very quickly to everybody in the network. And you could think, hang on, isn't that the same as degree? No, actually it isn't. I can have maybe just one friend. But for whatever reason, I'm sort of like the guy in the midst of things, or maybe I have 2 friends, who takes the least steps to reach everybody in the network. So there's now a different notion about centrality, and actually we call that closeness centrality. Closeness centrality is simply how close is an individual on average from all other individuals. And maybe now you see, okay, now this distance is coming to play, because essentially what we would do, we would look at each individual and look at the distance to everybody else, and then based on that, say whether individuals are close or far away from others. Closeness centrality is defined through farness. Farness is basically this idea how many steps on average does it take an individual to reach all other individuals. Yeah. If that number is high, it takes a lot of steps for me to reach everybody in this room. If this number is low, I have lots of direct connections to people in the room. Now that's sort of like the difference here. And then when the number is low, that means actually I'm sort of very close to everybody. So in that sense, farness in this case would be calculated relatively straightforward. Don't be put off by these formulas, seriously. Get the idea behind it, and the idea is very, very simple, it's very straightforward. It's really just going through for each individual. So for example, individual A, that guy, I count the distances, the average distance it takes from this guy to reach everybody else. And that guy is in the middle of it, so it takes on average just one step to reach everybody else. So that guy's farness is 1. While individual B, now you see this guy can reach individual A in 1 step, but to reach C in the fastest possible way, this guy needs to take 2 steps, 1, 2. And then to reach D, it's the same thing, like 1, 2, to get through A. And then you could calculate farness for that guy. In this case, it would be 7/4. So this guy is further away on average from everybody else. And then closeness is simply the inverse of that. So we take 1 divided by farness, and then we get numbers that range from 0 to 1. When you have a closeness centrality of 1, that means you have a direct connection to everybody. While when you have a closeness centrality that approaches 0, actually for 0 it's not defined, but when it approaches 0, that means you're really far away from everybody else. Okay, I had a little exercise, but I want to jump over this. I don't want to lose too much time on this for calculating this. You'll find it in the slides, so maybe if you want, you can do that by yourself later on. Okay, I also talked about betweenness centrality. Let me briefly mention that again. Betweenness centrality is this idea that maybe my maybe my importance in the network comes not from having lots of friends. Maybe it doesn't come from being close to others. Maybe it comes from being this guy in the middle that everybody else has to connect through. So when messages are being sent through the network, they float through me. So again, I might not have that many friends, but I'm just in such a position in the network that I could basically block a lot of information being sent between people. And that's the idea of betweenness centrality. Betweenness centrality is this idea on how many shortest paths does an individual lie. So in this case, the betweenness centrality of node A would be 6. You can go through a little bit because it would be like, okay, if B wants to reach C, B has to go through A. If B wants to reach D, B has to go through A. If B wants to reach E, B has to go through A. If C wants to reach E, they have to go through A. And if C wants to reach D, they have to go through A. So that would be 6. That's where this number comes from. It's like, and how many of those shortest paths does an individual lie? Well, for the other ones, there are no shortest path. Nobody cares about B if they want to reach the other individuals. So that's betweenness centrality, and then you can complicate things a little bit. Okay, how does this when there are more than one path, and so on. But I don't want to lose too much time about this. If you're interested in this, I'm actually writing a book about these kind of things right now. It's online as well, about how to do network analysis. But I want to move on. I want to press on and talk about this friendship paradox now. This friendship paradox, which is quite puzzling. So let's talk about it, what it is. You had this reading for today, and it is relevant for the exam, by Scott Feltz, Why Your Friends Have More Friends Than You Do. And basically, the message of that paper is, on average, your friends have more than you do. What does it mean? It doesn't mean that for everybody that holds, but if I kind of randomly select a person in more cases than in less cases, it is the case. So the average is higher. So I'm going to walk you through that a little bit, and now at the beginning also to give you a bit of the notion about why do we care about that. Well, here's our little Coleman boat that we had already so many times. It's about macro phenomena that we want to explain, and we want to explain it through the individuals that are involved. And my whole point was that networks need to be at the very core of it, because individuals depend on each other and so on. But networks also fundamentally affect the way how individuals experience the world. Fundamentally. You see the world through your social networks. You see news on Facebook from people who are your friends. Yeah? You don't see the news from people who are not your friends. You hear things from your friends that might make you believe that this is sort of what people think, but actually it's just your friends. Yeah? So in that sense, I'm fascinated by this, that our experiences of the social world are fundamentally biased by the social networks in which we are embedded. And the thing is, we are hardly aware of it. Because you don't have that eagle's eyes view. You don't see the bigger network picture. You just see your friends. And that's about it. Yeah? So it feeds a little bit into, Roland was talking about these echo chambers. You remember the lecture that we had about that, and polarization and so on. So it feeds into that. So networks affect the way the kind of people that we see. Yeah. And maybe you're getting where I'm going with this, because there's this whole literature out there that tells us that people that have more friends, they have certain attributes. They might be more attractive. Yeah? But that also means they are seen by more people. And then we are in the midst of the generalized friendship paradox. So anyway, but let me talk about the friendship, this article by Scott Feld first. So basically he said that, or the gist in his paper is that individuals with many friends, they show up in more friendship relationships. Imagine a guy who has 1,000 friends. Yeah? So each single one of these 1,000 friends has a friend who has 999 other friends. Right? So 1,000 people have a friend who has lots of friends. Now imagine a guy who only has 5 friends. And now only 5 people see a friend who has 4 other friends. Let me walk you through that in an example. So this is actually the example from the paper that you read for today, or from Scott Feld. A small little network with little names on it and so on. And now you see different numbers attached to it, and the numbers outside of the parentheses, that's basically degree centrality. That's what I just talked about. That's just how many friends do they have. Betty has 1 friend, there we go. That's sort of where this 1 comes from. Or Carol has 2 friends, 1 and 2. This is sort of where this 2 comes from. Or Alice has 4 friends, I will count it 1, 2, 3, 4. No? So that's sort of what these numbers are. Ignore the 1 in parentheses for a moment. That's basically just degree centrality. Okay, what are the numbers in parentheses now? Well, these numbers are actually the average number of friends that the friends of that individuals have. Let's look at Betty, because that's straightforward. So Betty only has 1 friend, yeah, who's Sue. And how many friends does Sue have? Well, 4. Right? So the average number of friends that Betty's friends have is 4. Or let's talk about Tina. Tina has 1 friend. How many friends do Tina's friends have? Well, Carol has 2 friends. This is sort of where this 2 comes from. Now let's look at Pam. So Pam has 3 friends: Sue, Alice, and Carol. Yeah. Alice has 4 friends, Sue has 4 friends, and Carol has 2 friends. If we would take the average of that, that would be 3.33. So this is sort of where these numbers are coming from, like the average number of friends that the friends have. But I have some more examples for that. And this is now directly out of the paper. That you read. This is basically this table with all the individuals. And there now we have a column with the number of friends, the total number of her friends, and the mean number of their friends. And here I have the example again. So Jane has 2 friends in this case, Dale and Alice. There we go. Jane has 2 friends. These are the 2 friends that Jane has. This is sort of where this number 2 comes from. Okay, Dale has 3 friends, and Alice has 4 friends. So in total, Jane's friends, Dale and Alice, have 7 friends. Dale has 3 friends, Alice has 4 friends. This is sort of where this number 7 is coming from. Oh, actually, I put a wrong number there. It's kind of a little confusing. It shouldn't be 2.35. It should be obviously 3.5. Because then the average number of friends that Jane's friends have is 3.5. Yeah? So we could do that. So this should be 3.5. So I'm typing. Okay, and then ultimately, we can look at how many friends two individuals have, and for each one of them we calculate what is the mean number of friends that their friends have, which is this thing. Yeah? And then we look at these averages. On average, people have 2.5 friends, but on average, the friends of people have 2.99 friends. So actually, in this case, I highlighted it a little bit earlier, and this is sort of, let me go back, this is sort of where these colors are coming from. For those guys, so 3 out of those seven individuals that I have here, or 3 out of those 8 individuals that I have here, they have more friends than their friends. But 5 individuals have less friends than their friends. So it's not half-half. Yeah. Why? Because the guys who have lots of friends, they are seen by lots of other people. So you have that as soon, and it's a very general thing, you have that as soon as there is some sort of variation in how many friends people have. Then the ones that have lots of friends, they are just seen very often. And actually behind this principle is a much more general principle. It's called the class size paradox, that actually students experiences school classes or lectures like this as much more packed than they actually are. Yeah? So if you go out and do a survey and say, is your lecture packed, or I don't know, seminar, sometimes you have that problem. Luckily we don't have that luxury, but sometimes there is that problem, that kind of the staff-student ratio is really bad, and I have to take care of lots of students at the same time and so on. And if you would go out, and actually most people would say it's actually very bad. Why? Because more people experience the class with lots of people. If I run a seminar with only 3 students, which is what I do sometimes, master's level courses, which is pretty cool, very intense, but then only 3 students see this have this experience of this very small class. In a similar way, people experience, let's say, when they go shopping in the city center, to be more packed than it actually is. Yeah. If I would ask you, okay, is it very stressful to go into Grafton Street? Yeah. People would say it's more busy than it actually is. Why? Because more people are there when it's busy. So more people get the experience that it's busy. When nobody is on Grafton Street, there are fewer people there to witness that, to observe that. So that's basically this thing that underlies this, which is sort of a little strange. Yeah. But that's, in a nutshell, the friendship paradox that we have, that if I would do that, that's what this paper was all about that you read, that the average number of friends that people have and the average number of friends that their friends have are different. And the second number is higher. Okay, now you can move on, and that's basically what I did in a paper a few years back. I looked at that in a more general way. So instead of just looking at degree centrality, now I looked at closeness centrality, I looked at betweenness centrality, I looked at eigenvector centrality. These are other forms of kind of thinking about importance of individuals in the network. And that's exactly what I found. I don't know why I have this other slide. So basically, I did this study where I took data from 14 American high schools, where everybody kind of noted who are their friends, and they kind of, this is sort of like a little example network that you see. This is a high school in the States. This is one out of those 14 high schools that I looked at. And now for each one of the individual nodes, I calculated all the centrality scores and compared it to the average centrality scores of their friends. And the result was as we expected, this is very straightforward, that this is sort of what we find, that on average, the friends, now I guess it'd be on the one axis, I plot for each individual, I plot for each of those 14 networks that I have, the average number of friends that individuals have. That's on the x-axis. On the y-axis, I plot the average number of friends that the friends have. basically I just do what Feld did in the paper with the last two numbers, 2.5 and 2.99. Yeah, and then I plot them against each other on the x and on the y-axis. They do exactly the same thing. But now what you see is that this is sort of now for, it's not just a fluke, but it's sort of like for, I don't know, in this case for all of those 14 schools, it is the case that the average number of friends that friends have is higher than the average number of friends that people have. We find the same thing for betweenness centrality. Yeah? So it's not just that your friends tend to have more friends, but they also seem to be more important in terms of being those guys who are mediators, who kind of connect people, where information has to go through. We also find a little bit for closeness centrality and for eigenvector centrality. So basically you can extend that. I have another slide, let me go back to this. So I want to talk about this one a little bit, because we do find this friendship paradox, maybe in one area where you might be most familiar with to it, is actually Twitter. It's very prevalent in Twitter. And there we call it the virality or activity paradox. It's exactly the same thing. And what it refers to is that on Twitter, 98% of the people have fewer followers than the people who they follow. So what does it mean? It means like take a person and look at, you have your Twitter account and you follow, I don't know, 1,000 people, or maybe you follow 200 people, and you have certain followers as well. Yeah? Maybe some of your friends, and let's say you have 50 followers or whatnot, yeah? And so on. And most of the time, actually for almost everybody, it is the case that the average number of followers that the people have who you follow is much higher. Why is that? Because you follow those crazy Twitter stars that have millions of followers, right? So those guys are seen by lots of people. They're also more likely to be seen by you as having lots of followers, because you are more likely to be connected with them, because they are in more relationships in a way. So, and that kind of leads to these very weird situations, because you can take that idea, you know, like now employ it to, I don't know, another thing that's kind of fascinating is when you study Facebook feeds, news feeds, for example. It seems to be the case that in other people's lives there's so much more happening. Yeah? And then you think, God, my life sucks. You know? There's not much happening. But actually, this is a result of exactly this. That those people where a lot of things happen, you know, they tend to be more connected, and because of that, they are seen by more people. And when you think about how individuals, you know, we talked about individuals, you know, they experience their social environment and so on, and that is sort of like the foundations for how they act. You know, we talked about segregation and all these kind of things, you know, where they look at the people around them and so on. So now you see the importance for this, because if it is fundamentally biased, what I see through my people around me, right, because of these networks, because of these paradox, then I might behave very different from how I would normally behave if I would be aware that what I see on Facebook is not representative for the real life, yeah, or what I kind of see on Twitter is not representative for the real world. It's just obviously, I don't know, I'm more connected to popular people, so there's sort of different things happening in their life. And if you kind of then take that one step further, you know, then you would say, okay, hang on. So actually, what we need to do is to tell people to make that distinction between the people who they follow, where they see they have certain characteristics and certain attributes, and their own expectations for how the world looks like and how they look like in this world. And that brings me now to the study that I did. Well, actually, there's two more, so let me hurry up a little bit. So, because this can be very powerful, this paradox, to use. Yeah? So one study looked at that for the distribution of, or for the spread of diseases. Basically what they did, you know, it's like famous guys, Christakis and Fowler, you know, they looked at how quickly does the flu spread in the population of students. You know, actually they looked at the students at Harvard, they were both at Harvard at the time, so they measured how many of the students are sick. Yeah? They have the flu. And then they looked at random people that they sort of collected. But then so this is sort of the one thing, and this is sort of represented by the red lines that we have here. But then on the top of that, they kind of, instead of just going for the random people, they asked the random people whether a random friend of theirs is sick. So you take a random friend of a random person, but that person is not random anymore. That person is more likely to be central. Why? Because the person has lots of incoming connections. So you're more, if you have 1,000 friends, you're more likely to be selected as this random friend than if I only have 5 friends. Then only 5 other people can select me. Well, if I have 1,000 people can select me. So basically what they found was that when they looked at the outbreak of the flu, their predictions were much more accurate or much more precise and earlier on when they kind of looked at the random friends of random people. Why? Because they are more likely to be in the middle of things, right? And then you could say, okay, well, they are in the middle of the network, so these are these super hubs that kind of spread the disease, where things go through. So it's not just a fluke, but there's sort of like real-world application to it. And I did this study, so I extended this a little bit. And because we do know for the longest time in network analysis that there's a relationship between certain attributes of individuals and their network position. So we know that important individuals, they tend to be innovative, more innovative. They tend to be better in their job search. When you sort of have the right networks, you tend to perform better, and people even tend to look better. So there's sort of we call that a correlation or a relationship between how many friends people have and how attractive they are. And these associations, they can come about in many different ways. It can be through adoption. Let's say people are important in the network to begin with, and because of that, they adopt certain attributes like opinions. But it could also be the other way around. Attractiveness you cannot force that in a way. Yeah? So people might be more attractive to begin with, and because of that, they get more friends. There are 2 different mechanisms for it, but at the end, you have these associations there. Okay. Now, what happens when we take that idea, that sort of attributes correlate with network positions, and we merge it with this friendship paradox, that on average, your friends tend to have more friends than yours? Well, basically, then we come up, this is sort of like this most recent paper that I'm working on, that your friends are likely to have more friends than you. That was what Scott Feld already wrote about, right? But your friends are likely to have certain non-random attributes as well. And it's actually pure logic why that has to be the case. If, as soon as you have this correlation, and as soon as you have a network where not everybody has the same number of friends, these 2 things come together. So I actually did a little study on that. So let me talk about that very briefly. So actually I did a study on Facebook on this. So I selected randomly, which was actually really funny, to randomly scrape Facebook profile pictures. You wouldn't believe what people have as their Facebook profile pictures. So I think I looked at 10,000 pictures. So for a week I was just going nuts, because there's the amount of superheroes or pop stars or babies or dogs or kittens or whatnot that people have as their Facebook profile picture. So anyway, so I randomly selected at the end 1,000 profile pictures. And then for each one of those, I randomly selected one of their friends on Facebook. And I scraped, at the end I wrote a computer program that does these kind of things. I scraped then the profile pictures of the random friend as well. So I had like a random group and I had the friends group. Each one I had around 1,000 profile pictures in it. And then, I set up this website. It's called wholooksbetter.net. It doesn't exist anymore, so it's actually gone now. Yeah? And I had my students in Stockholm play this game. They loved it. They kind of, I don't know, nowadays, Tinder, this is how it goes. You click left or right. In this case, it was more like a comparison. Which one of these 2 guys looks better? So I had like a crowdsourced attractiveness score. So I had lots of students in Stockholm University do that with me. And now your intuition would tell you, hang on a moment. The people in the red group, they should be equally likely to be attractive as the people in the green group. Like the random group, the randomly selected people, or the randomly selected friends of those people. Your intuition tells you there shouldn't be a reason. But the friendship paradox actually says there is a reason. So a randomly selected friend of a random person is not random anymore. That person is more likely to be better connected, and because there is this association between being better connected and attractiveness, that person is more likely to be attractive as well. And that's actually what I found. So actually my results were, that in 53% of the times, like the random friend of a random person was better looking than the randomly selected person, while it's only 43% of the time it was the other way around. And then you can look at why that is the case. And actually the reason for that is because in that data there is a correlation, as we would have expected, between attractiveness, in this case the crowdsourced attractiveness score that my students in Stockholm generated for me, and the number of friends that people have. So ultimately, this is the reason why your friends on average don't tend to have just more friends, but why they also tend to be more attractive. On that note, no reading for next week. Okay, thanks very much, guys.